Tech, and today is with us. And there are very few things in astronomy that I wouldn't comment with him, since he knows a little bit of everything, which is amazing. We have fantasy football together, and he's working on a tier system on restaurants too. I don't know, you're talking about tier system today? No, that's next seminar. Next seminar. Today we're going to talk about globular cluster, and you have the floor.
All right. So the mic is on. It's white. Okay. Thanks for the invitation to give a talk here. It's always a pleasure to have the opportunity to come out to Santa Barbara from Pasadena. And it was great talking to everybody today who I chatted with this morning. My primary research goal is to constrain the details of compact objects, black holes, neutron stars, white dwarfs, in dense star clusters. So clusters similar to the globular clusters that we observe in the Milky Way. So the primary tool I use to sort of attack this problem is N-body simulations. So in the past roughly 10 years, the sort of N-body simulation community has sort of for the first time become computationally capable of actually doing full star-by-star realizations of million body systems. So this has really allowed us to, by performing full N-body simulations of these globular clusters, make a lot of predictions on the theory side for applications of these compact objects, et cetera. So within this sort of idea, there's been a number of recent observations also in the past 5-10 years that sort of have implications for this topic. So I'll talk about a few of these, both electromagnetic observations that hint at compact object populations and clusters. And then also what has been sort of a key theme of my work in the past few years is this application to gravitational wave astronomy. So as I will argue during the talk, we now think that it's quite plausible that a fraction of the binary black hole mergers that have been observed as gravitational wave sources by LIGO could have formed dynamically in dense star clusters similar to the globular clusters in the Milky Way. Okay, so just to sort of get us on the same page, I want to sort of discuss some sort of characteristic properties of globular clusters. So the Milky Way has roughly 150 globular clusters that are observed. So these have been observed and very well studied for many decades. The vast majority of these clusters are found roughly spherically distributed in the halo of the galaxy. The typical offset from the center is around 10 kiloparsecs or so. And then you also have a subpopulation of clusters that are found in the disk of the galaxy. So we think there's probably roughly 50 or so globular clusters over here, hidden from our view by the galactic bulge. So probably something like of order 200 total globular clusters in the Milky Way. So globular clusters are some of the oldest stars in the galaxy. So sort of a characteristic age to keep in mind is around 10 billion years. Old, although some of the Milky Way clusters are even older than this, 13 billion years or so. Associated with their very old ages, these are generally very low metallicity populations simply because they were formed earlier on in the universe. A nice sort of fiducial number to keep in mind is around 10% of the solar metallicity, although some of the Milky Way clusters can be as low as 1% or even lower of the solar metallicity value. So globular clusters are generally massive as far as clusters go, especially compared to open clusters, which are far more numerous. There are many thousands of open clusters in the Milky Way, but they typically contain only hundreds of thousands of stars. Typical globular cluster contains hundreds of thousands up to even millions of stars. And they're also very compact. So a typical half light or half mass radius of a globular cluster is of order of parsec. And a really nice thing I sort of like to usually say is that, so of course, the distance to the closest star to our sun is Proxima Centauri, also about a parsec away. So within a typical cluster, there are millions of stars bound within the volume enclosed by this distance to Proxima Centauri. So this very clearly shows how dense these objects are. And this high stellar density is what makes these objects very rich dynamical environments. So to give a little illustration of this is an example of one of our N-body simulations of these clusters. And you can see as a result of these many dynamical encounters, these frequent flybys, gravitational interactions between neighboring stars, the orbits of the star and the clusters are constantly changing. They're constantly being perturbed. Their velocities are constantly being altered by these many encounters with other objects. And the cumulative effect of these mini gravitational encounters is basically what allows these systems to relax and settle into these spherical configurations, which is where they get their names. So, as I said, the Milky Way has of order a couple hundred globular clusters. It's now pretty well understood that globular clusters are common features of all galaxy types. This goes from the lowest mass dwarf galaxies, which contain anywhere from a few to maybe a few tens of clusters. Spiral galaxies, again, like the Milky Way and Andromeda, contain generally of order a few hundred globular clusters. And then also the largest elliptical galaxies, for instance, M87, contain thousands to, in the case of M87, tens of thousands of globular clusters. And very recently, thanks to HST and also most recently James Webb, we've also begun to observe globular clusters of very distant galaxies. So this is just one of, maybe some of you have seen this, it's kind of a famous circulating image from JWST. This is one of the deep gravitationally lensed fields from James Webb. And zooming in here on one of the galaxies in this field, you can see these small little spherical blobs, which we think are actually some of the most distant, youngest globular clusters that we've yet observed. And then just for reference, you can see comparing to the HST image of this field, you can see that sort of the resolving of these globular clusters is uniquely abled by JWST. So one of the sort of key science goals of James Webb that I'm particularly excited about is actually observing these very high redshift globular clusters. And this sort of is allowing us to sort of piece together what is really one of the biggest uncertainties in this field, which is what the old globular clusters in the Milky Way looked like closer to the time of formation. The details of the formation really set a lot of the processes for determining, for example, the black hole merger rate, et cetera, as I'll discuss in a minute. Okay, so what I want to do next is sort of look at one of these younger globular clusters and look at this population of stars and sort of talk about the implications for the number of black holes that might be formed. So for a typical globular cluster, again, with roughly 1 million stars at birth, for a typical initial stellar mass function, like a Krupa or saltpeter IMF, you can expect roughly 1,000 or a couple thousand black holes to form. So roughly 1 black hole per 1,000 stars in the cluster. These are simply forming from just the normal stellar evolution of the most massive objects. So because clusters are generally low metallicity, as I said before, these massive stars have reduced amounts of mass loss through stellar winds on the main sequence and also during the giant phase. And as a result of this, the black holes that form in these low metallicity clusters, we think are generally on the massive side as far as stellar mass black holes go. So the typical mass of these black holes is maybe around 30 to 40 solar masses is our expectation. So this population of roughly 1,000 black holes forms relatively early on in the host cluster's evolution within the first maybe few to tens of millions of years. And very quickly after formation, the black holes are going to sink to the center of their host. So this is a natural consequence of dynamical friction, which is operating in any sufficiently dense stellar environment, whether it's a globular cluster or a nuclear star cluster, et cetera. And the timescale for this dynamical friction, this mass segregation, basically is sensitive to the density of the environment. So dense objects like globular clusters have mass segregation timescales of a few 100 million years. So on the timescale of the life of a cluster, 10 billion years or more, this mass segregation occurs pretty quickly. So relatively early on, you form this sort of dense subsystem where roughly 1,000 stellar mass black holes congregate in the center. And within this very dense subsystem of black holes, as a result of these high densities, the black holes are going to dynamically interact with one another and also interact dynamically with other stars. And this naturally sets the stage for the formation of binary black hole pairs, potentially similar to the ones that have been observed by LIGO. Okay, so this next slide is a kind of just a fun little animation that's zooming in on the center of one of these clusters. And this is basically an example of one of our N-body simulations and sort of showing the encounters that are happening pertaining to these black holes. So just to draw your eye to a few things, again, the sort of first thing you'll kind of notice is that very often the stars come in, happen to wander close to a black hole, and then get flung out with a very high velocity. So this is a sort of natural consequence of the fact that black holes are more massive than the average star. This means that as they interact with stars dynamically, they naturally transfer energy to the stars. So as a result, basically, stars occasionally will be entirely ejected from their host cluster through these black hole encounters. But more generally, it means that the black holes basically dynamically heat the stellar bulk. They basically cause the stars to naturally segregate outward, and this is actually the mechanism that allows the black holes to segregate inward. Another thing you'll see, I'll start it over, is that occasionally you'll see the black holes themselves get flung out at really high velocities. This is because as black holes interact with each other, they also kick one another dynamically. And because typical escape velocities of globular clusters, maybe of order of 50 kilometers per second or so, are relatively small as far as astronomical environments goes, it's pretty straightforward to actually kick black holes out. So actually, we expect as a result of these encounters, the number of black holes in the cluster decreases throughout the evolution of the cluster. And the final and these are the potential sources of the gravitational wave signals that have been observed by LIGO. Okay, so the next thing I want to do is sort of talk about some actual observational evidence of these processes happening in our simulations. So for a number of decades, actually, it was thought that basically these dynamical processes that operate concerning black holes would be so efficient that by the present day ages of globular clusters, all of the black holes would have been dynamically kicked out. And this was also sort of complemented or motivated by observational indications, because up until recently, although there are many neutron stars observed in clusters as millisecond pulsars and X-ray binaries, there was no black holes that have been observed. But in the past roughly 10 years, there's been a growing amount of observational evidence for black holes in clusters, which has sort of motivated us to think that actually most clusters contain black holes throughout their entire lives. So observational evidence number one. So this was from an observation in 2018. A team using the MUSE instrument on the VLT observed through radio velocity measurements a black hole main sequence star binary, detached, so not interacting, not transferring mass, in the center of one of the Milky Way globular clusters. NGC 3201 is the name of the cluster. So from the sort of radio velocity measurements, you can constrain the M sin I of the hidden companion. In this case, you can see here, highlighted in yellow, the companion mass has a minimum mass of around 4.4 solar masses. So quite clearly, it's not a neutron star or even a binary neutron star. It is almost certainly a black hole. And this was actually the first ever black hole, stellar mass black hole, to be observed dynamically through dynamical measurements. So since this initial detection in 2018, this same team actually found, through follow-up observations, 2 additional dynamically measured black holes in the same cluster, also simply detached black hole main sequence star binaries. And then there's been also a number of these detached black hole binaries observed recently in the galactic field, for example, through Gaia observations. So these sort of dynamically observed black hole binaries are sort of a new addition to this field of stellar mass black hole science. So in addition to these detached dynamically inferred black hole binaries, there's also been in the past, I think 2012 was the first one of these, so 10 years, a number of black holes observed in X-ray binaries. So these are black holes accreting from a binary companion. And the idea here is that through the X-ray and radio observations, you can infer or argue that the accretor in these systems is a black hole as opposed to a neutron star. So the basic idea is, so looking at those sort of so-called fundamental plane of black hole activity, the ratio of radio to X-ray luminosity, objects up on this part of the track where all these globular cluster sources are found, we argue are black hole accretors. So there's around 10 or so of these X-ray/radio black hole candidates in a handful of different Milky Way globular clusters. So in addition to these sort of individual black holes that are observed in clusters. There's also observational clues hinting at the sort of underlying population of single black holes that can be observed. Most of the black holes are not found in binaries in clusters. We expect most of them are single objects. So obviously it's a little bit harder to observationally identify isolated black holes. So these larger populations of black holes can be constrained by looking at their cumulative effect on the large-scale structure of the host cluster that they're living in. So let me explain basically how this works. So this is sort of a typical Milky Way globular cluster. And on the bottom here, I'm showing the surface brightness profile or the density profile of the cluster. So as you can see, of course, based on sort of just looking at the optical image of this cluster, the brightness is increasing toward the center. And then within what we call the core radius of the cluster, roughly the innermost parsec or so, you can see the brightness flattens out. So this flat component in the brightness profile is what we call the core of the cluster. And the vast majority of clusters in the Milky Way have this very clear core component. This is sort of indicative of, again, just the core of the center of the cluster. But roughly 20% of the clusters in the Milky Way are what we call core collapsed. So in these, basically as far in the center as we can resolve the brightness profile, the brightness increases all the way into the center. So instead of having this core, we have this cusp structure in the center, and we call these roughly 20% of clusters core collapsed. So as self-gravitating n-body systems governed by gravity, basically all globular clusters naturally evolve toward a core collapse configuration. This is just because energy naturally flows for gravitating systems from the core out into the outer parts of the halo of the cluster. And actually, based on the relaxation times we infer from observations of Milky Way clusters, we actually would expect most of the clusters should have undergone core collapse. So it's a bit of a sort of a mystery why what we observe is actually opposite, where most clusters are in fact not core collapsed at present day. This sort of implies there must be some other energy mechanism operating that's delaying the onset of core collapse in the majority of clusters. And the sort of consensus opinion that has emerged, and this has been complemented by, again, these n-body simulations, is that these populations of black holes in the centers of clusters are this source of dynamical energy that delays core collapse. So let me sort of walk through how this works. So this is basically showing the evolution of the brightness profile of a cluster for n-body simulations that take into account these black hole dynamics that allow black holes to naturally be ejected from the center of the cluster over time. So when you have a large population of black holes early on in the cluster, hundreds of thousands of black holes, they heat the cluster significantly, and you have this very large flat component in the brightness profile, a very large core. And as the number of black holes decreases, the brightness profile of this cluster clearly becomes more cuspy, eventually tending toward this core collapse configuration where there's an absence of a core altogether. And this corresponds with when the cluster has essentially ejected dynamically nearly all of its black holes. So essentially we expect that the clusters that have the largest cores are the ones that still have most of their black holes in their centers. And the most concentrated clusters, the core collapse ones, are the ones that have dynamically processed through their black holes and have ejected nearly all of them.
But what's the mechanism? They're scattering stars out, so they're not letting them accumulate in the center?
Yep, that's basically right. So again, because the black holes are constantly gravitationally interacting with the stars, and because, again, the black holes are more massive, they naturally inject energy into the stellar population. When you're injecting energy into stars, every time the stars try to come into the center, they get basically ejected out. Only once the black holes have been ejected can now the massive stars, start to sink, is the idea. But again, because most of the clusters in the Milky Way are not core collapsed, we expect that most clusters currently still have dozens to hundreds of black holes in their centers. And to sort of connect this back to NG3201, this cluster where we observe these detached black hole binaries, this plot here is showing basically the surface brightness profile in yellow of this particular cluster with the black holes, compared to n-body simulations with many versus very few black holes. And again, you can very clearly see the n-body models that most accurately capture the density distribution of this cluster are the ones that still have large numbers of black holes in their centers. So we argue that, in fact, it's not a coincidence that this particular cluster is the one in which these black holes have been identified. It's actually a natural consequence of the fact that it has such a large core because there's a large underlying population of black holes in the center.
Technically, question about your n-body simulation. So it's not really an n-body simulation in the sense that you don't resolve like n square gravitational forces, right? You have some averaged potential from the rest of the system that the thing is going in. And do you resolve the dynamical friction?
Yeah, so it's an n-body simulation in the sense of we're accounting for all n stars within the simulation, but it's not a pure n-body. This is a specific question, I think, for others in the audience, but it's not a pure n-body simulation in the sense of it's not doing the actual n by n gravitational encounters of every star with every other star. So those simulations you can perform those simulations for million body systems, but they're computationally intractable to do in large numbers. So
my question was, in the simplified versions, do you resolve the dynamical friction sufficiently high? Because that is because of fluctuations in the potential, right?
Yeah, I mean, as best as we can tell, I mean, it compares very well with direct n-body simulations in terms of matching the effect. I can show you some comparisons that maybe afterwards if you'd like to see. Okay, so sort of all of these pieces of evidence hopefully at least convince you somewhat that I think there are very strong indications that most globular clusters have black holes throughout their lifetimes. So when you have populations of black holes in the cluster living in some environment of a known density, it's a fairly straightforward dynamical calculation to calculate the rate of binary black hole mergers. So the presence of black holes within these clusters naturally implies the formation and the onset of these binary black hole mergers. The question then is simply, what is the rate of these mergers? Potentially, how does it compare to the rates that have been observed by LIGO? And also, what are the properties? What are the masses, et cetera? So this sort of transitions to sort of part two of this talk, which is now the implications for LIGO and the implications for forming gravitational wave sources.
Before you move on, okay, to ask questions.
Of course, yes, please.
So this 20%, is that consistent with the lifetime of ejecting the black holes from this age distribution in the Milky Way? Do you expect 20% to have ejected all of their black holes?
Yeah, so and we think that the key distinction which allows this number to be 20% versus say 50% or something different is the distribution of initial cluster sizes. So the denser the cluster is initially, basically the faster its dynamical clock, the faster it evolves dynamically, and the faster it reaches a core collapse configuration. So we expect, based on our sort of best understanding of initial cluster sizes based on looking at young massive clusters in the local universe, we expect this naturally then leads to, at least on the modeling side, we're able to naturally reproduce this fraction of 20 versus 80%.
Those 20%, there's no evidence for the X-ray radio objects in any of those 20% core collapse?
So that's right. And this probably, I probably won't have time to get to this, but there's actually there's many interesting other connected observations. So those 20% of clusters have a very well observed overabundance of millisecond pulsars, neutron star X-ray binaries, white dwarf binaries. And we expect this is specifically enabled because they have ejected most of their black holes, and now the neutron stars and the white dwarfs are the most massive objects. So they themselves sink to the centers and then undergo their own increased dynamical encounters. So I think that sort of also hints at this connection between the black holes and the underlying cluster structure. Okay, so transitioning to the gravitational wave implication. So probably most of you have heard now. Yeah, question. Yeah.
near the center of the host halo. Is that somewhat similar to what's happening in simulation near the like central part of the surface brightness compound?
Yeah, I think that the problem with overmerging is related to the fact is a resolution artifact where the details of the merger aren't resolved in those types of simulations. Whereas it's a little bit different here because our mergers, the details of whether a particular binary merges is actually not really dynamics related. It's simply related to the gravitational wave in-spiral time, and that's very well resolved. That's simply just a very simple calculation that can be performed in the n-body simulations. So the n-body simulations simply allow you to assemble the binary black holes in the first place, and that is very well. The simulations are able to do that very well. The actual merger is determined by the gravitational wave in-spiral, which is, I think, a little bit different from the scenario you're talking about. Other questions before I maybe? Yeah.
So you mentioned that basically that the black holes are segregated in the center by roughly 1 million years. So I guess like
100 million years, yeah. But
yeah, more so. So like black holes, new black holes from supernovas that are not factored because everything exploded already.
That's right.
Okay.
That's right. Yeah. There's a kind of unrelated topic of whether or not there's primordial mass segregation in clusters where massive stars are preferentially born closer to the center to begin with. But it doesn't have a big effect because, again, the mass segregation timescale is so short compared to the cluster lifetime.
The simulations have mergers of regular stars.
Yep.
Is that a strong effect?
Is it a strong effect on?
I mean, you could get new black holes from more massive.
So yeah, so that's a actually very interesting question. And yeah, I'll actually talk about that a little bit later. Yes, and there actually are observational indications of stellar mergers in clusters. That's actually something that's very well observed. So we know stellar mergers happen, and that I think also sort of implies that black hole mergers are likely occurring. It quite clearly shows that there's very close n-body interactions between stars happening in clusters. Other questions before I transition? Okay. Okay, so yeah, as I was saying, I think most of us are familiar with this idea now. As of almost 10 years ago, we have sort of unlocked this new ability to observe objects through gravitational wave emission, thanks to the LIGO Gravitational Wave Interferometer. And now we have Virgo and Kagra online as well. So since this first detection back in 2015, there have now been many dozens of detections of binary black holes, binary neutron stars, black hole neutron star binaries detected via gravitational waves. So some of you may have seen a similar plot. This is basically showing in blue all of the black hole binaries that have been observed as gravitational wave sources sorted in order of their stellar mass. So you can see that there have been sources observed from as low as a few solar masses all the way up to over 100 solar masses in terms of the masses. So even with this very large catalog of gravitational wave sources that we now have, a very fundamental question is still uncertain, which is what is the specific mechanism through which these binary black holes are assembled? So there have been many different theories that have been proposed. This sort of gives a quick summary of a few of the main ones. The two big ones I'm going to talk about, or that I'm going to mention today, are isolated binary evolution, where basically a pair of black holes are born, a pair of black hole progenitors are born in a massive stellar binary, but then evolve, potentially undergo a common envelope or other binary mass transfer episodes, and lead to the configuration of a sufficiently compact black hole binary to merge within a Hubble time. So this is sort of the isolated binary evolution scenario. And then the alternative scenario that I'm going to focus more on is this dynamical assembly scenario, where through the mechanisms that I've been describing so far, you form a dense cluster of black holes in the center of very dynamically active environments that leads to dynamical pairing of black holes after they evolved as stars. And again, leads to the assembly of sufficiently compact sources to lead to mergers within Hubble time. There have been a number of additional scenarios proposed, ranging from scenario in AGN disks to even non-astrophysical scenarios like primordial black holes. I'm not going to have time to get into these, but I can ask you later if you want to hear about any of them. Okay, so what I want to do next is sort of talk about the specific types of dynamical encounters within these centers of these globular clusters that actually lead to the formation of black hole pairs and eventually black hole pair mergers. So the key initial first step is you need to have a way to assemble black hole binaries. So these could form in principle through just primordial binaries in the cluster, just from simply the massive stellar binaries that evolve into massive black hole pairs. But even in the absence of primordial binaries, you're going to naturally form binaries and clusters through three-body formation mechanisms. So the idea here is if you have three objects come close enough together, two of them can become bound at the expense of the third, and you're left with basically a compact binary that could potentially become more compact. So when you have sufficiently compact binaries and clusters, they naturally undergo additional dynamical encounters with other objects in the cluster. So these form these temporary resonant states of 3 or 4 bodies, like I'm showing here. And the consequence of these dynamical binary mediated encounters is for compact binaries to essentially become more compact. This is sort of intuitively can be understood because compact binaries are going to naturally want to settle into a more stable state, which is more compact, deeper gravitational potential well. So as these black hole binaries, once they're formed, undergo additional encounters, they naturally become closer, become more compact. Now, as these binaries become more compact, as their semi-major axis is reduced, conservation of energy arguments implies that they are also dynamically kicked further out into their host cluster. So basically, as the orbital velocity of the binary increases, as the binary shrinks, the binary receives an increasingly large dynamical recoil kick. So as you can see here, as the binary, one of these binaries undergoes additional encounters, it gets kicked out further and further into its host cluster before mass segregating back through the dynamical friction effect I talked about earlier, until eventually its recoil velocity exceeds the escape velocity of the cluster and it's ejected. So once the black hole binary is ejected, then we can sort of ask whether it's compact enough to merge within a Hubble time. This is the primary way that black hole binary mergers are assembled in clusters. So actually, most of the black hole mergers don't occur in the cluster themselves. They're formed and sort of prepared for merger within the cluster, and then they actually merge after they've been ejected. But there are also a subset of mergers that actually occur inside the cluster themselves. This is because during these extended series of encounters, occasionally you can acquire a sufficiently high eccentricity to have a very prompt merger, and these could occur inside the cluster. So based on n-body simulations of clusters that take into account all of these effects and take into account the sort of matches to the brightness profiles of Milky Way clusters like I showed before, we can compute the merger rates of these black hole binaries and potentially then also compare them to the rates that have been inferred from LIGO observations so far. So this here shows in blue, it's a little faint here on this, but you can see it. This is the range and merger rates inferred from through the third observing run from LIGO. So you can see in the local universe, LIGO predicts a black hole merger rate of around 20 mergers per gigaparsec cube per year. And then these black curves are showing the rates inferred from n-body simulations for a few different sort of characteristic values of initial cluster radii. So as you can probably guess intuitively, the more compact the cluster is initially, the more dense it is, the more mergers you get. So you can see that the most compact clusters produce the most mergers.
Okay, but
Yes.
so the LIGO Virgo rate is the inferred rate from population analysis. So that is the rate. If I ask what is a random merger that contributes to that rate, it's a low mass merger, right? Because in the population analysis, they fit the mass function of the binaries as well as the overall number. So most of the binary species, the 30-30 solar mass mergers, don't contribute the majority of this rate.
So what would be the typical?
I would say like 10% or even lesser of the LIGO rates in these plots is 30-30 solar mass merger.
Well, what would be the typical mass you would say then for the?
It would be like, few, like, 5 solar mass, 5 solar mass. Something. We see very few of them because they are not very loud.
Okay, yeah.
Or horizon distance is very small.
Yeah, I see what you're saying.
So, but then I remember your arguments was that the typical globular cluster mergers are 30 solar mass.
Mhm.
They can't directly, it's like apples to oranges, right?
Yeah, at some level, yeah. This is mostly just to simply say that, again, because there's a range and uncertainty of the LIGO rate, this is simply demonstrating that the overall merger rate is in principle comparable to the LIGO merger rate. I understand what you're saying, though, that, yeah, and I'm going to show that on the next slides. When you start to look at the details of the masses, I'm not trying to claim with this that,
No, I'm checking.
yeah. No, thanks for the clarification. So anyway, the punchline of this is that in principle, the rates that we infer from M-body simulations are on the same order of magnitude compared to what's been inferred from LIGO observations so far.
What are the various black curves?
Yeah, so these are different initial cluster radius values. So this is sort of the key parameter that determines the total number observed. And this range in radii is basically roughly our sort of the range you would expect based on looking at young massive clusters in the local universe. So we expect most globular clusters are born with virial radii or half mass radii within this range. Now, the exact distribution of clusters within this range is uncertain, just because we observe clusters when they're old, not when they're young. So the contribution from these different curves is not clear from the outset, but this gives just sort of a rough idea of the range, the range and uncertainty of the rates. Okay, so one other sort of clue related to your question, or sort of the corollary of your question, is that there's a subset of LIGO mergers that are very massive objects. So these are the ones up on the right-hand side of this plot that have masses in excess of 50 solar masses. So these occupy a region of Kremer space known as the parent stability mass gap, where essentially we expect that for massive stars that reach sufficiently high temperatures in their cores, electron-positron pair annihilation leads to basically a thermonuclear runaway and actually prevents the formation of black holes entirely within this very massive range. So from stellar evolution models alone, we actually expect there to be a gap in the black hole mass function above roughly 50 solar masses. So the detection of these massive objects by LIGO was somewhat of a surprise from a theoretical point of view, because we expected objects like this to not necessarily be present astrophysically.
Defining EM black holes and EM neutrons.
Yeah, I didn't really get into that so much, but basically the EM black holes are all of the black holes that have been observed through like X-ray binary measurements. So these are, yeah, that's sort of an alternative way to infer black hole masses based on those.
Expect any significant SED at longer wavelengths?
Yeah, so I mean, a lot of these have been also observed in other wavelengths as well, where you're not actually observing the accretion, but like you can observe the companion star itself, and then, yeah. So I don't know if that answered your question, but
I was talking to Nancy at Caltech. She was interested in much longer wavelength observations in the near infrared in particular. Unclear to me how that plays out here.
yeah, I haven't thought as much about the X-ray binary, so I don't know if I can give a better explanation of what probably Mansi said, but yeah. Okay, so getting to these specifically massive black holes, these also may sort of provide clues as to a dynamical contribution or a cluster origin for some of these sources, because in clusters, there are a number of ways to potentially circumvent this parent stability process that may limit the number of these massive black holes that might be present for a typical black hole population. So this again is just showing the distribution of masses that's been observed for the LIGO Virgo population in green, and then comparing to the distribution of masses we would expect from a typical cluster population. This gray background is showing roughly, it's very uncertain, but this is roughly an indication of the parent stability mass gap boundary. And you can see that both distributions naturally extend into this gray background where the parent stability is expected to set in. So there are a number of potential mechanisms that would operate in clusters that would allow you to form these very massive black holes that might explain the contribution of these to the overall LIGO population. So 2 examples. So I hear you mentioned massive stellar mergers. So in principle, massive stellar mergers are happening before black holes actually form in the clusters. This potentially would allow you to form very massive stars early on that might allow you to collapse into more massive black holes. If these massive black holes then acquire a companion, they can merge and potentially form very massive parent stability gap mergers.
Stellar merger would collapse to a black hole. It wouldn't suffer from the same mass gap. It wouldn't.
Yeah, so there's lots of different things that can happen for a merger product. The basic idea people have argued, maybe we can talk afterward.
Okay.
It's kind of a specific thing, but I can tell you about it. Another way massive black hole binary mergers can be assembled in clusters is that because these are living in a dynamical environment, when you have a single black hole merger occur, for example, a merger of 2 lower mass, say 30 or 40 solar mass black holes, that merger product could potentially find a new companion and merge again. So these extended series or hierarchical series of black hole mergers potentially is giving you another way to assemble more massive black hole binary mergers and clusters. And interestingly, the contribution of these more massive black hole mergers predicted from n-body simulations, roughly a few % of all the mergers expected, is comparable to the number of these massive black hole mergers that have been observed by LIGO. And then there are a few other potential indications of cluster dynamics that might be used to constrain the contribution or lack of contribution of dynamics to the potential formation rate of LIGO sources. So this includes both spins and also eccentricities of the mergers. I'm running a little short time, so I'm not going to talk about this too much. The one key punchline I want to mention is that the current distribution of spins that's been inferred from LIGO observations so far, as I'm showing on the right here, shows quite clearly that there's a preference for aligned spins in terms of the overall population. So this maybe suggests that the entire population is not coming from a dynamical origin where, because of the randomness of these encounters, you would expect a more isotropic or random distribution of spins. So ask me about this later if you want to hear more specifics about this. And then this plot here is sort of a nice little summary or sort of tie the bow on this gravitational wave section. So this is basically showing the expected number of black hole mergers and other types of compact object mergers expected through gravitational wave observations over the coming years, coming decades of the field as new detectors come online. Advanced versions of LIGO, the Voyager mission, Cosmic Explorer, et cetera. So we expect that over the coming years, the number of mergers that are able to be observed is going to approach millions, which is certainly very exciting from the perspective of constraining the details of these black holes and also potentially their formation scenarios. Okay, so I'm running out of time and I want to leave time for questions. So I'll mention one other thing in just a few minutes and then I'll finish up. So sort of building on this idea that, clusters contain black hole populations and they contain sufficiently dense environments to lead to interesting black hole dynamical interactions. We also expect clusters to be rich sources of electromagnetic transients in addition to the gravitational wave transients. So during these sort of resonant binary encounters, like the ones that I showed before, you have many close flybys between stars that happen. And as a result of these many encounters and these many sort of flybys, you have many chances to actually have close enough encounters for stars to come into contact and actually merge with each other. And we talked about this a little bit before. There's actually a large amount of observational evidence for these stellar mergers occurring through these so-called blue straggler stars observed in clusters. So these blue stragglers are basically near turn-off mass stars that lie blueward of the main sequence turn-off in clusters. And there are many of these blue stragglers, dozens, in some cases even hundreds, observed in basically all globular clusters in the Milky Way. Our sort of current idea for how these objects formed is that basically they're main sequence turn-off stars that merge, become rejuvenated through the merger itself, and then appear hotter, or they actually are hotter and then appear bluer relative to other stars of comparable ages. These blue stragglers are hints at these stellar mergers actually happening in globular clusters. So if indeed clusters contain black hole populations and these black holes are mixing dynamically with stars, as there's a lot of evidence for, this means that occasionally you'll have black hole star collisions or black hole star tidal disruption events. And instead of forming blue stragglers when you have a black hole involved, these potentially would lead to a more catastrophic event where the star will be completely destroyed or tidally disrupted, and this potentially could lead to a bright electromagnetic flare. So this plot here is just simply taking, again, a set of n-body simulations that take into account all of these processes I've been discussing, and simply showing every scatter point here is an example of when a black hole collides physically with a star. So the orange points here are the giant branch stars. You can see the mass of these decreases over time simply because the turn-off mass is evolving over time. All of the black points are the main sequence stars, which generally are all below the main sequence turn-off, as you'd expect. And then you also have a very small number of white dwarfs. So not surprisingly, main sequence stars are the dominant thing that the black holes collide with, just because there are by far the most of these objects. Giants have a larger cross-section for encounters, but they live a lot, much shorter, so it's harder to have the collisions for them. So overall, the prediction is that roughly you would expect a collision rate of around 10 to maybe 100 per gigaparsec cube per year of these tidal disruption events. So quite a bit less than the core-class supernova rate for reference, but certainly a high enough rate to potentially produce a number of these events that might be detectable in the local universe. So I'll show one little hydro simulation of an example of one of these encounters, and then I think that'll be a good place to wrap up. So this here is a hydrodynamic simulation of a 2 solar mass star interacting with a 10 solar mass black hole. So the black hole is the white circle. And there are sort of a few sort of key differences between these stellar mass black hole tidal disruptions and sort of the classic supermassive black hole tidal disruption, like is shown in that little picture over there. So in a supermassive black hole TDE, the stellar mass is basically negligible compared to the black hole, which means the tidal disruption radius is very large compared to the stellar radius. And this means that basically the star in general is completely destroyed after the first encounter. In this scenario where the tidal disruption radius is comparable to the stellar radius, you're generally only strip a small amount of the stellar mass. And this means that part of the star is actually going to survive that initial encounter, become bound to the black hole, and then continue to undergo a few different orbits. So you saw in this case, you had 3 or 4 repeated partial disruptions that happen on a timescale of days or weeks that ultimately lead to the full disruption of the star. And the final outcome of these encounters is essentially for most of the mass to become bound to the black hole. And essentially you're left with a very thick rotating torus of material, or a thick accretion disk that then slowly accretes onto the black hole throughout the subsequent evolution of these objects. So very quickly, I'll just sort of talk through the electromagnetic signature you would expect for these. So again, you have a very thick accretion disk of material that accretes onto the black hole, produces a very bright high energy flare, likely predominantly X-rays. But because the accretion flows are actually very highly super Eddington, you actually lose a lot of mass from the disk that just becomes unbound in the form of a spherical wind. So this dense circumstellar wind that's surrounding the disk actually is going to absorb most of this high energy accretion energy and then re-emit it as a thermal spectrum and produce a reprocessed transient or an interaction powered transient, which is going to be generally optical or UV in terms of the peak wavelength. So we expect these are roughly of order 10 to the 40 up to maybe 10 to the 44 ergs per second, depending on the accretion details. Certainly bright enough in principle to be observed in large numbers by GTF, Rubin, transient facilities, etc. Okay, so I think I'll wrap up here. I'll skip ahead on slides that you aren't going to get to hear about, and I'll go right to my conclusions. So the main punchline is globular clusters. We expect to have very rich populations of compact objects. I didn't get into so much neutron stars and white dwarfs, but there are a number of other exciting implications as far as transients that would be produced related to these things. And the next few decades are really going to be, I think, a great time for constraining the details of these compact objects, both with new versions and updated gravitational wave detectors, and also with all sky surveys, new upcoming radio surveys, etc. So thanks again for the invite, for listening, and happy to answer some questions if people have any.
Okay, that's some questions through the talk, but we definitely have time for a few more. So I have a question like about a stellar disruption event. Like, what's the time scale that you expect the event to happen? Like you mentioned, like several orbits. Like, what are we talking about?
So the dominant time scale in these is just going to be the viscous time of the accretion disk, which is of order in probably days. So they should be relatively fast evolving compared to, for example, the supermassive black hole TVs, where the dominant time scale is the fallback time for material to return to pericenter, which can be much longer. So they should have rise times of probably of order a day or a few days.
On the lookout, I guess.
Yeah.
Enjoy.
Yeah.
So based on your N-body simulations from earlier, do you have an estimate of how frequent these tidal disruption events should be?
Yeah, so roughly 10 to 10s per gigaparsec cube per year, so about 1% of the core collapse supernova rate.
I guess I still don't have a good image of like if you're
For Milky Way, roughly
Right.
1 per million years,
Thank you.
which is,
No,
yeah, so, what's that?
anytime now.
Yeah, exactly.
So still, if you looked at the Virgo central galaxies cluster system, which has tens of thousands, it's still not really feasible.
Yeah, so even in Virgo, though, yeah, so just looking at Virgo and hoping to find one of these is also probably not a very good idea. You really need to go to more larger survey volumes, but because they're likely definitely bright enough, you should be able to detect these out to a few hundred megaparsecs with like Rubin, for instance, or even out to maybe even a gigaparsec with Rubin.
Supernova comparable. You see supernovas, we should be able to see that.
Exactly.
Any other question?
So you mentioned the detection or possible detection of the systems in JWST. Have those detections already given you some interesting information?
Of looking at the young clusters with JWST. Not so much yet, just because it's sort of now, I think, just sort of in the stages of identifying as proof of principle that these young clusters can be observed. So hopefully as a larger ensemble of these are observed in sort of population properties that will provide constraints on the birth details.
No more questions. I guess we can thank Kyle again.
Good.
You know, Nancy.
Yep.
Yeah, so. And this is very interesting. Okay, man.